If you've spent any time working in AWS, you likely know the core trifecta: EC2 for compute, S3 for storage, and IAM for access. But knowing how to spin up a server does not make you a cloud architect. The real separation between an intermediate user and an expert lies in exactly how you handle massive enterprise scale. Look at this schematic. This is a functional standard AWS environment. We have a single AWS account, one virtual private cloud, or VPC, a few EC2 instances, and a standard RDS database communicating out through the public internet. It works perfectly for a small application. Watch what happens when we force this basic architecture to scale. If we acquire a new company and need to deploy 50 more VPCs, the standard method of VPC peering creates a chaotic, tangled web of connections. Management becomes severely complicated, and security vulnerabilities immediately pop up across overlapping deployment nodes. Standard architectures collapse under the actual demands of an enterprise. They can't handle multi-account governance, massive localized data gravity, or highly specialized compute workloads. There is a common misconception that enterprise scaling simply means provisioning more VPCs and selecting larger EC2 instances. That approach just takes a fragile system and makes it bigger. To move past these limitations, we are going to map the definitive advanced AWS roadmap by tearing down that completely broken web and building a robust, scalable enterprise architecture entirely from the ground up. The first step on this roadmap requires a complete shift in operations. An architect cannot simply manually provision their resources. They must instead rely on automated systemic frameworks to enforce order before a single server is ever launched. The foundation of this new build starts with the AWS account itself. Operating a massive enterprise out of a single account is an inherent risk. We have to move to a multi-account strategy, utilizing AWS organizations to centrally manage billing and strictly control access via service control policies across the entire company. This animated diagram shows our new perimeter. Instead of one account, we now have an overarching AWS organizations bounding box that securely wraps multiple isolated AWS accounts. Surrounding that is a secondary, heavy shield labeled AWS Config. AWS Config shifts us away from manual security audits. In an environment this large, you cannot manually check every new resource. Config acts as a continuous inventory tracker, automatically monitoring configuration changes and enforcing operational rules across every single account in real time. With governance lockdown, we look at the internal network. Connecting two VPCs directly with VPC peering makes sense. Connecting 200 creates an unmanageable point-to-point administrative burden, where a single routing error can break the system. We fix this by moving to a hub-and-spoke topology. Notice how the chaotic web of peering lines is deleted and replaced by a central transit gateway hub. This gateway functions as the core routing engine for the entire infrastructure. It neatly connects thousands of VPCs, meaning a new VPC only requires one single connection to the gateway to access the entire network. But our internal network still has a vulnerability. It communicates with on-premises data centers over the public internet. For sensitive enterprise workloads, the variable latency and security exposure of the open web are unacceptable. We eliminate that exposure by establishing a dedicated physical connection. This solid line represents AWS Direct Connect, a private fiber optic link from an external data center straight into our transit gateway, bypassing the public internet entirely. To finalize this foundation, every component we just built must be scripted. By utilizing CloudFormation for infrastructure as code, we can version control our entire setup and replicate it automatically in another region within minutes, establishing a highly robust disaster recovery strategy. Automated governance and centralized secure networking form the strict bedrock of our enterprise. Only after this infrastructure glue is fully implemented can we securely host and scale specialized data services. With the network stabilized, the next stress point is data storage. Traditional relational databases, like standard RDS setups, eventually hit physical hardware limits when processing millions of concurrent requests. Look closely at this updated data layer. We are replacing those standard RDS instances with DynamoDB. The metrics here show it operating at single-digit millisecond latency regardless of scale. DynamoDB is a fully managed NoSQL key-value database. Its distributed architecture allowed it to handle the massive read and write demands of modern applications without buckling under the weight of traditional relational table joins. Storing this volume of data introduces strict compliance requirements. Security at this level mandates that you maintain absolute centralized control over how that data is encrypted at rest. We manage that encryption through the Key Management Service, or KMS. This lock icon represents KMS centrally generating, distributing, and auditing the cryptographic keys that secure the entire DynamoDB storage layer. Yet, migrating historical data into this secure layer often hits a physical wall. This is the concept of data gravity. If you have petabytes of legacy data sitting in an offline facility, it is mathematically impossible to transfer it all over a standard internet connection in a reasonable timeframe. When bandwidth fails, you bypass the network completely. AWS solves this with the Snow family. You ship the data on ruggedized, secure hardware devices from an offline facility directly into an AWS data center. By upgrading past relational database bottlenecks and solving the physics of offline data gravity, our environment is equipped to handle intense distributed workloads operating outside the traditional data center. We can now expand our architecture far beyond the core AWS region to support remote operations, manufacturing plants, shipping fleets, and industrial sensors operating in the physical world. This diagram maps that physical expansion. We have a sprawling network of remote sensors routing their data streams straight into a central node called AWS IoT Core, located strictly inside our cloud boundary. IoT Core operates as the brain of this network. It manages the complex authentication, security protocols, and message routing required when billions of connected devices attempt to communicate with your infrastructure at once. But forcing every remote device to transmit every single piece of raw data back to IoT Core consumes massive bandwidth and introduces unacceptable latency for systems requiring split-second decisions. To fix this, we push compute power directly to the physical devices themselves using AWS Greengrass. Watch the data flow now. An AWS Greengrass node sits locally next to the industrial sensors. It intercepts the raw data, processes it on-site in real time, and sends only the crucial condensed insights back up to the AWS cloud. By executing local compute at the extreme physical edge, we drastically reduce network latency and ensure that remote industrial applications continue operating effectively, even if their internet connection drops. At this point, our architecture is pulling in diverse sets of data from everywhere: transactional data from DynamoDB, telemetry from IoT Core, and massive historical archives via Snowball. Managing this influx as raw, unstructured files creates an organizational nightmare. This animated schematic shows how we structure that data. The disparate data streams are funneled into a central Amazon S3 bucket. Overlaid on that bucket is AWS Lake Formation, organizing the incoming streams into a structural grid and piping the data outward to query engines like Athena and Redshift. Building a centralized data lake manually is highly complex. Lake Formation automates the entire process, handling the ingestion, structuring, and precise security policies, so your analytics tools can query the data immediately. A structured, centralized repository provides the mandatory data foundation required to deploy any form of artificial intelligence. With our data prepared, AWS offers two distinct paths for machine learning. You can use SageMaker to build, train, and deploy customized ML models from scratch, or you can leverage turnkey services like Personalize to integrate real-time recommendation engines without a dedicated data science team. Regardless of the path, running machine learning models continuously in a production environment typically demands expensive GPU hardware, which rapidly inflates operational costs. We apply a targeted cost optimization strategy here. Watch as an elastic inference GPU module fractionally attaches to a standard EC2 instance, pulling models from the data lake. Instead of paying for full, dedicated GPU instances that sit idle half the time, elastic inference allows architects to provision exact fractions of GPU acceleration, significantly reducing the cost of running machine learning inferences. For architectures exploring decentralized ledgers, AWS blockchain templates operate on a similar principle of abstraction, providing rapid deployment frameworks so teams focus on application logic rather than wrestling with node infrastructure. The critical takeaway is that advanced capabilities like AI and machine learning are not standalone magic tricks. they only function effectively when resting upon the rigorously structured, centralized data lake foundation we just built. Look back at where we started. That fragile, tangled web of intermediate cloud resources has been entirely replaced by a fully realized enterprise architecture. This completed topological map visually defines the 3 distinct phases of a cloud architect's journey. We have divided the environment into 3 zones: the core, the data layer, and the edge. Phase 1 required mastering the infrastructure clue. We established central governance across multiple accounts, locked down internal routing with transit gateways, and mandated infrastructure as code. In Phase 2, we solved the physics of data gravity. We bypassed the internet to transfer physical data, replaced relational bottlenecks with highly performant NoSQL, and organized the raw outputs into a tightly governed, unified data lake. Finally, Phase 3 pushed our compute power out into the physical world with localized edge processing, and utilized our structured data to fuel cost-optimized, intelligent machine learning applications. Mastering AWS does not come from memorizing a list of individual tools. The definitive path from a basic cloud user to a true AWS cloud architect lies in understanding how to architect this systemic, interconnected progression.